Here's a fact that surprises people. When a transformer computes attention, the slow part usually isn't the math. It's the memory traffic. Standard attention writes a giant score matrix out to the GPU's main memory and reads it back, and that shuffling is the real bottleneck. FlashAttention-2 from Tri Dao in 2023 gives the exact same answer as normal attention, just far faster by never writing that matrix at all. Let's see how. So before the fix, look at what standard attention actually does versus what flash attention does instead. Normal attention takes your queries and keys and builds the full n by n score matrix, one entry for every pair of tokens. That matrix gets written out to slow high bandwidth memory, then read back for the softmax, then read again for the values. All that reading and writing grows with the square of the sequence length, and it's where the time goes. Flash attention refuses to ever store that big matrix. Instead, it fuses the whole operation and works in small tiles that stay inside the chip's fast on-chip memory. Because it's aware of where data lives and how expensive each move is, it does the exact same computation while the giant matrix simply never exists in slow memory. Now, how does it get the right answer without ever materializing that matrix? Follow one tile through the engine. First, it pulls a small block of queries, keys, and values up from slow memory into fast on-chip SRAM. These tiles are tiny, so several of them fit in the fast memory that sits right next to the compute units. Nothing large is ever moved. Then, inside that fast memory, it computes the attention scores for just this block. It's a little patch of the full matrix, but this patch never leaves the chip. As soon as we're done with it, the numbers are consumed and thrown away. Here's the clever bit. An online softmax keeps a running total as each new tile arrives, rescaling what it already has so the final normalization is exactly correct. That trick is what lets it process the sequence in pieces yet match full attention to the last digit. Finally, once every tile has folded into those running totals, it writes out only the finished output. One clean result goes back to memory. The enormous intermediate matrix was never stored, so the traffic drops from quadratic to linear. So what did FlashAttention-2 add on top of that, and why does it matter? 3 ideas carry it. Start with the most important promise. This is exact attention, not an approximation. You get bit for bit the same result as the standard formula, so there's no accuracy trade-off to weigh. It's purely a smarter way to run the identical computation. Being aware of the memory hierarchy is the whole game. By tiling into fast on-chip memory and never writing the big matrix, it turns a memory-bound operation into one limited mostly by actual arithmetic, which is exactly what you want on a GPU. The second version then sharpens the parallelism. It divides the work more evenly across the GPU's warps and thread blocks, trims the operations that aren't matrix multiplies, and parallelizes along the sequence itself, roughly doubling the original and reaching a large fraction of the hardware's theoretical peak. Alright, let's carry away the essentials. Standard attention is slow mainly because it writes a huge n by n matrix to slow memory, and that traffic, not the math, is the bottleneck. Flash attention processes attention in tiles that stay in fast on-chip memory, using an online softmax so the big matrix is never stored. The second version improves the parallelism and work partitioning across the GPU, roughly doubling speed and reaching close to hardware peak. Best of all, it stays exact, giving normal attentions result with linear memory rather than quadratic. Want more AI internals unpacked this plainly? That's exactly what Standarity.com is for. See you there.